Okay, welcome back once again. This is the third video in the set regarding review of antiderivatives and indefinite intervals. We're going to finally apply the concepts, terms, and rules we've just reviewed on some specific examples. So, when I had face-to-face classes rather than doing a gateway portfolio, we had gateway tests where you earned very little partial credit. You had 10 questions involving integration techniques, and you needed to get, or you should have gotten a good passing score before the end of the course, and you had to take it repeatedly until you did. Well, the first question on all of those gateways looks something like the following. These are just applications of memorized antiderivative rules. So, one key thing, I can break up integrals over addition and subtraction, and I can move constants out. So if I break this in a couple of steps, it's the integral of 2 cosine of x, but I'm also going to bring out the 2. And then in a similar way, I have minus an integral of 4 square root of x, but I can bring out the 4. Similarly, I'll bring the 3 out of the 3 over x, so I have 1 over x. I'll bring the 6 out of the 6 e to the x, and I'll bring the 4 out and have it as 1 over 1 plus x squared. One other thing I want to do is rewrite my square root of x as x to the 1/2 power. So now I apply the appropriate memorized antiderivative rules. The antiderivative or an antiderivative of cosine of x is sine of x. Or in general, I instead think of whose derivative is cosine of x. Again, the answer is sine of x. Minus 4. I have a power rule here. Instead of bringing the power down and reducing it by 1, I'm going to increase the power by 1. I'll write it as 1 plus 1/2 and divide by the new power. Here, I cannot do that this way. This is an x to the negative 1, and if we recall, my power rule won't work when the power is a negative 1. Why is that? Because the new power would be 0, and dividing by that power would be division by 0, which is a very bad thing as the universe implodes on itself anytime someone succeeds in dividing by 0. Since we're still here, no one has ever successfully divided by 0. Anyway, when you integrate 1 over x, you're asking yourself, whose derivative is 1 over x? And then you're like, that's right. The natural log's derivative is 1 over x, but I've got to be very careful. This x is allowed to also be negative, so I've got to slap some absolute values around it. So the integral of 1 over x is natural log of the absolute value of x. When you integrate e to the x, you say, whose derivative is e to the x? Well, the derivative of e to the x gives me e to the x. Lastly, what happens when I integrate 1 over 1 plus x squared? You must think, whose derivative is 1 over 1 plus x squared? And this is one it's a derivative we put to memory. It's the derivative of the arctangent of x. Key thing to remember when you're done, this is an antiderivative, but I've got to cover my base to any that works, so any constant can be added to that thing and give me my answer. This is my final answer. I would prefer that I would write 1 plus 1/2 as a 3/2 power, and dividing by 3/2, which is the same as multiplying by 2/3, but for sake of room, we'll leave it as this. Similar kind of idea, but now, one more time, we'll break this into pieces. We'll factor the 3 out, and I have an integral of cosecant squared of t dt plus an integral of pi squared dt plus 16 an integral of, we'll rewrite the cube root of t as t to the 1/3 power minus, bring the 9 out, times 1 over t squared dt minus an integral of the sine of t dt. Please notice, I am very careful, and you need to be as well. This is the period to the end of the sentence started by integrals. You must specify what you're integrating with respect to. If you go, it's obvious, it's the variable in here. Well, it's obvious maybe here. You have to say, whose derivative gives me cosecant squared? I'm like, oh, wait. The derivative of a tangent of something is the secant squared of something. The derivative of the cotangent of t is a negative cosecant squared of t. So I need to counterbalance that negative, and I have a cotangent of t. But what happens if you get to this and you have an integral of pi squared and there's no d whatever because somebody was sloppy or careless? What are you integrating with respect to? What variable shows up in your answer? It isn't pi, because pi is not a variable. It is a rational or irrational number that corresponds to the ratio of the diameter of the circle to its radius, or a multiple of that. Anyway, keep in mind, this thing is just a constant. So when I integrate a constant, or I think whose derivative is a constant, it's that constant times my variable. What is my variable? Somebody need to tell me with what that variable was by that d fill in the blank. So anyway, please don't forget the d blank. Plus 16. Integrate t to the 1/3 power. I use the power rule, which now says increase that power by 1. 1/3 plus 1. Looks like it's 1/3 plus 1. Divide by that new power. Minus 9. This is not a 1 over t. We cannot say my integral is a natural log of t squared because the derivative of the natural log of t squared is 1 over t squared, but the chain rule says times the derivative of the inside, which is 2t. This is not what I have here. So I must rewrite as t to the negative 2, and then apply the power rule and get t to the negative 2 plus 1 divided by negative 2 plus 1. Lastly, whose derivative is the sine of t? It will be a negative cosine of t plus a c. We'll simplify our answer since I've got the space. Negative 3 cotangent of t plus pi squared t plus 16. 1/3 plus a 1 is 1/3 plus 3/3, or 4/3. Divided by 4/3 is the same as multiplied by 3/4. The negative 2 plus a 1 is a negative 1 power. That negative 1 is also in the denominator. Minus a minus is a plus. Cosine of t plus c. So actually, I'll make one more step to simplify a few other terms. 3/4 of 16. 4 goes into 16 4 times. 4 times 3 is